since the topic is timing. So my name is Harald Hauglin. I'm the Time Lord of Norway. Or I'm chief engineer, chefingeniør, responsible for time and frequency metrology at Justedvesenet, the Norwegian Metrology Service. So I'll be talking about GNSS timing, interference detection, and countermeasures. So I will try to give some introduction and then try to sum up some of the things we've learned actually working on this topic. Okay, just a brief introduction to Justedvesenet. You may notice Justedvesenet stickers on the weights in the stores or on the gas pumps. So Justedvesenet is the Norwegian Metrology Service in English. So it's a national metrology institute of Norway, and responsible for weights and measures in Norway, and responsible for this law on units of measurement, on measurements, and normal time. So I'm not going to read the Norwegian purpose of the law, but just for the topic today, GNSS interference detection and countermeasure. Why should we be involved in this? And really the purpose of the law says that the law should also take care of interests or systems that are worth protecting, that are based on the measurements. So it's not just economic measurements for sales and so on. Okay. So JV, short for Justedvesenet, has a timing laboratory, so it's a national timing laboratory. We have currently, 5 clocks. We contribute clocks to UTC. And UTC is the world's common time scale. It's based on a number of atomic clocks. About 500 clocks are regularly contributing to the computation of UTC. So Norway has 4 that we contribute, and we generate a national UTC timescale, and the goal is that the clock offset between our timescale and the UTC proper should be less than 10 nanoseconds. So and we do research and development on secure network timing. We're working on high precision protocols, in particular together with grid operator.net in the COSEC time projects. We're also involved in digital substation timing, which is based on precision time over networks. And also for the topic today, the GNSS interference detection and countermeasures. So resilience against jamming and spoofing. Okay, just to brag a bit. At least this graphic shows the improvement we did at the end of June this year, essentially switching the timescale generation from cesium clocks, which are noisy, which is in the beginning of the year, to our currently best clock, which is called a passive high-gen maser, which is much more predictable and less noisy. So the goal is at least to maintain a timescale with an offset of less than 10 nanoseconds, and also with redundancy, so we can actually generate parallel timescales with more or less the same properties. So for the topic of GNSS interference, I actually was sort of dragged into this by being asked to contribute to a vulnerability assessment back in, well, it was published in 2013, but the work started in 2011. And then I realized I don't really understand how GNSS works, and I don't really understand how GNSS discipline clocks work. But anyway, we contributed to that assessment. We also contributed to the current so-called P&T strategy, so strategy on positioning, navigation, and timing. And lately, we also had really fun contributing to the world's largest GNSS hackathon, if you like, the Jammer Test 2022 at Andøya, where we were tasked to provide the GNSS spoofing signals, which were broadcast. So the national communications authorities actually had given the permission to broadcast such signals in open air. And that's actually a rare, very rare occasion outside of military exercises. So, and Thomas, who is here, we brought a brand new signal generator, and well, we made it work. Okay. So, so what have we done in terms of R&D on, well, P&T security? So, GNSS in particular. Essentially, we've had 2 master's projects, one in 2016 and one with Thomas now submitted this spring. So the first one looking into how can you actually build a better GNSS discipline clock by making it smarter. And Thomas was working on how can you make tests for testing how such clocks perform. And then, as I already mentioned, we've also been working since 2016 with StartNet, trying to take a system over, well, look at what are really the timing needs and how can they be solved in a really secure manner. So some of the experiences from doing that is also summed up in a paper, which you can find on that link if you're really interested, or you can send me an email. Okay, accurate time from GNSS. I'll try to explain this without too much detail. So GNSS means Global Navigation Satellite Systems. So GPS is one type of GNSS, right? The European Galileo is another type. Then you have the Russian GLONASS, and you have the Chinese Baidu. Those are the global systems. But the satellites are essentially very accurate clocks in orbit, where in addition to the clocks being accurate, you know very accurately where they are at any moment. And this you can use. So in the simplest case, not to determine where we are, but to determine what your clock is, you can do what I try to illustrate here. That is very accurate clock in orbit. You know where it is. It sends out a timestamp message. At exactly 12 o'clock, I sent this message. Then you have your antenna. And you know where your antenna is, right? Which means you know the distance from your antenna to the satellite. Then you can, using your own clock, which is not accurate, you can time the arrival of that transmission from the satellite, right? And you know the distance to the satellite, and you know the speed of light or the speed of radio propagation. So you know what to expect, how much the signal should be delayed. Then you can compute the difference between what you measure with your clock and what you expect. And that gives you an estimate of how wrong is your clock. And you can take that number and correct your clock in various ways. So there's a lot of technical detail in exactly how is this information coded into the signal and how is it decoded and so on. But in the simplest case, this is what you need to get accurate timing from GNSS satellite. So you need a known position, and you need essentially one satellite. What you may also need from the satellite, which is also encoded in the signal, is an estimate of the offset between UTC, the common timescale, and the GNSS system time. So typically that offset is a few nanoseconds plus an integer number of leap seconds. So once you have that information, you can take your observation and compute what is the error of your clock with respect to UTC. And if you really want to be accurate, you can characterize your receiver chain. So you can characterize the delay through the antenna and the cable and the processing in the receiver. And typically, that delay is something like 5 nanoseconds per meter of antenna cable, and something like 30 to 100 nanoseconds within the receiver itself. Okay, if you don't know exactly where your antenna is, and typically that's the case, unless you've done a survey. And this is the general case when you use GNSS to determine where you are. Then you need to observe at least 4 satellites, because then you have 4 unknowns. You need to determine a 3D location, and you need to determine a clock offset. And you should note that if you had a very accurate clock, you only need to see 3 satellites. But no clock in a GNSS receiver is sufficiently accurate that you would be happy with the position you get. So when you determine your position, you always also have to determine the clock offset of your receiver clock. Okay, I hope this is clear enough. So the reason, or since you get accurate timing from GNSS, that's the reason why you see GNSS antennas on stationary objects like buildings and on mobile phone base stations. It's not to know where they are, but it's as a source for accurate time and frequency for various applications. And for a large number of applications, you find a dependence on GNSS timing. And here is a list from a UK review from a few years back. We'll look into one of the examples, power grid synchronization and maintenance. But you should also know that in emerging applications, this is a few years old, right? New telecoms, 5G, but 5G is here, right? And the way 5G is built in Norway, there is the base stations, not just for within one operator's network, but also between networks, between operators within the same region, have to be synchronized to within a microsecond or so. And for some advanced 5G applications, much better than a microsecond. So that's a really critical use of timing. So, well, why does the power sector, the grid operator, have a reliance on accurate timing? This may be a simplification, but this is really the 2003 blackout in the Northeast USA and parts of Canada. I don't know how familiar you are with the geography of United States, but it's not a huge bay, right? It's a densely populated area. So this was a huge blackout, which was caused, I think, by something as simple as a tree falling over one power line, right? And then you have a cascade of events. unfolding over something like 15 to 20 minutes, right? Until you had this huge blackout that lasted for hours and cost a lot, right? And in the aftermath of trying to figure out what did happen when and how could this have been prevented, one really clear lesson was that we need a much better and much faster overview of what's actually going on in the system. Once you have that, you can think to start build systems that automatically shut things down to prevent a small failure to cascade into a large blackout like this. And part of the input into such a system are accurately timestamped measurements from sensors around the grid, which in practice means a reliance on GNSS clocks to timestamp the measurements. So what one realized is that the systems one had did not give updated information, and the procedures to handle faults were typically based on manual intervention. One thought one had ample of time to react to disturbances. I think, in fact, this picture is from a nuclear power station control room. But I like the relaxed attitude. But clearly the blackout was a wake-up call, right, for the power industry. So then what has been built in the US and in Norway and in many countries are sensor networks. And some of the sensors are called phaser measurement units that timestamp electrical measurements in various parts of the grid. And then you can collect those data from various parts of the grid, and you can rapidly calculate where is the power flowing now. And then you can determine that in some part of the grid you're reaching some kind of breakdown threshold. You can do things to stop the breakdown from happening. So, but one key information in this whole scheme is the timestamp, because if the timestamp is off for one sensor, you get an incorrect estimate of how much power is flowing. Right. So that's really information that you really need to protect. And that's why I claim that PNT, in this case timing security, is a subset of cybersecurity. So for the security of the whole operation, it's a key information asset. So you might think, well, then GPS should be, and the GPS disturbances should be considered among the common attack vectors you need to protect yourself against. And maybe this audience knows better than me where I would go to find such vulnerabilities listed. But I went to the MITRE organization. I hope this is a good choice. And just search for GPS. Right? And I got a good list. I think something like 70 entries. But almost all of them are with, I would say, conventional security breaches in applications that just use GPS position data, with one exception that I could find. And it's the one highlighted here, which is for a particular arbiter GPS substation clock. But really, this is really arbitrary. That's this one particular clock is singled out because this is a really common vulnerability. So it says that this clock allows remote attackers to cause a denial of service or disruption via crafted radio transmissions that spoof GPS satellite broadcasts. So this is an attack vector in the radio frequency domain, spoofing a signal from satellites. So spoofing is just one example of GNSS signal interference. So one thing to keep in mind is that GNSS signals are really difficult to protect because the satellites are typically 20,000 kilometers out there. And they send with something like 100 watts. Okay, it's with an antenna that is not uniform, but it covers the Earth. But still, it's a really weak signal, right? And with few exceptions, it's unencrypted, right? For military use, there is an encrypted GPS code. And also with Galileo, there will be encrypted civilian service. But well, it's not available for Norwegian users, and it's not something that's easy to imagine being widely used. So it's weak, unencrypted, and in addition, you need antennas that are outdoor in order to receive those weak signals. So you cannot physically secure your infrastructure into some kind of mountain bunker, right? The antenna has to be outside. So that's a real challenge. And then one could classify the signal interference in, I've done 3 types of interference. So one it's often referred to as jamming, but it could be intentional or unintentional radio frequency noise that may block your GNSS receiver from getting any signal and getting any solution at all. Or it may just give a degraded solution, a poor solution. Then there's this word spoofing that we saw in the CVE, right? So spoof means mimicking, right? So it's transmission of GNSS signals that do not originate from the satellites. So in this case, one could distinguish between simple or incoherent spoofing, so signals that are very different from what you get from the live sky. And you can have more advanced or coherent spoofing, where the signals being transmitted actually mimic what you get from the live sky. And then the last category is often referred to as meaconing, but rebroadcast of live sky signals. So you have one antenna that receives live sky signals, and then you rebroadcast it to some other target antenna. There are genuine uses for this. So for instance, for airplanes moving into hangars where they don't have GNSS reception, it's actually very useful for the systems to have rebroadcasted signals from an antenna outside. So that's meaconing. And it's a genuine use of meaconing. But if you use it for attacking something, it's in some sense a bit, it's a powerful thing to do, because even for encrypted signals, you don't have to break the encryption to just rebroadcast it. And for a timing receiver, then the rebroadcast means you get a signal delay. So your timing solution is off at least by that delay. Okay. So perhaps in a more hacker language, at least blocking a GNSS solution by transmitting noise could be viewed as a denial of service attack, right? You don't get a solution. And spoofing, you inject your own signals that are being interpreted by the receiver, could be called code injection. And for genuine uses like testing systems, that would not be malicious. But for an attacker trying to manipulate and distort, that would be malicious code injection, right? And the same goes for meaconing. Could be considered some kind of code injection. So let's just look at some effects of jamming or signal degradation. This is from Thomas's master thesis, and we just didn't really disconnect the antenna cable properly. Just put it next to the antenna connector. So there was some signal, but not very good signal. And we just said, what? Why is it telling us that we're not at Justevesnes Kjeller, that we're kilometers off? And then when we also looked at the timing solution that you got out from such a really marginal signal, the timing solution is also many microseconds off. So things like this would mess up 5G synchronization, for instance. And it would also mess up these phase measurement units in the power grid. So the lesson learned from this is that signal degradation from either a weak signal or from noise that interferes is not really a denial of service. It may be a degradation of service, degradation of the signal. Here's another example from this earlier master's project where we had not planned to actually disturb anything other than, well, we did things like wrapping the antenna in aluminum foil. But this is not the case. This happened that night. We were just monitoring what's the normal function of the GNSS timing solution and position solution and so on. And what we saw is that instead of a clean cut, good signal or good solution or no solution, also in this case we saw a degraded solution. And in this case we actually had a very stable clock running that was steered by the GNSS timing solution. Then we can look at effects of incoherent spoofing. This is actually from the, I guess, pilot, the precursor to the Andøya Jammer Test 2022. There was a smaller exercise in Skibotn, northern Norway, in 2021. So at one point there was essentially a signal generator turned on that produced a GPS signal corresponding to being out in the sea 12 days back, right? And this is the effect on one of the timing or GPS disciplined clocks or time servers we brought along, right? So it said signal is available, it's master, it's locked. So everything is okay. Okay, it says the offset is 66 hours. So that's a huge jump for a time server. And I think if we just had continued transmitting this signal, it would eventually have adjusted 12 days back in time. And happily, and it also reports it's actually at 70 degrees north and 10 degrees east. So, how can we detect this kind of signal interference? Well, in one example I showed from this accurate clock and from the monitoring that we did, we see that we get changes in height, for instance, that do not correspond to where, well, the antenna is stationary. We know it should report some height within some noise in the solution. And the same goes for speed. It's stationary. It should report some speed with some noise, but on average 0. And here there's a sudden jump in speed. And we see there's accompanied by a drop in the number of satellites it's actually using to compute both position and speed and time. And it's obviously also with a incoherent spoofing example. We know that we are not suddenly 12 days back, right? And we're not here now and then suddenly we are in Kuala Lumpur, right? But those really simple checks on reality are not built into many devices, right? So in particular for GNSS timing devices that are usually stationary, you can just build in a lot of consistency checks just in knowing that you're in the correct position. You essentially have no velocity. There are no large jumps in the clock solution. Well, you know that time flows forward, not backward. And in particular, one thing that was done in this master's project from 2016 is that we put up 2 antennas so far apart that they never report they're in the same location. If those 2 antennas actually receive spoofing signals from one spoofer, they would report the same position. And it's really tricky to try to fool both antennas to report a position which is not the same. Then that's a really difficult thing to do. And it's really easy to set up 3 antennas, which it's impossible in practice to fool all 3 with fake signals. And so there are some really basic consistency checks you can do, and then you can check on signal consistency, that the signal strength is consistent with signals being transmitted from 20,000 kilometers out there and not from a powerful transmitter on ground. You can check that the information you get now is consistent with what you expect, so that you don't suddenly have satellites suddenly reporting they're somewhere else on the sky, for instance. So there are many consistency checks you can do there. And then lately there have also been, now there are open signal authentication mechanisms built into at least the Galileo signals, which relies on that they're encoded with some private key, and your receiver gets the public key, and you can compute. You can make sure that the signals you receive are from the satellites and not from some signal generator that does not have the correct private key. And we're testing this mechanism now. It's not in full deployment yet, but it's in the public test phase. So that's the detection part. Now, what are the countermeasures? You can use better internal clocks, and you can use smarter clock controllers. So better internal clocks means you can maintain good timing even without, for a long time even without steering from GNSS signals, if it's done in a smart way. So this again is our details from this 2016 master's project, and these are, well, every pointer is every second, I think. So what you see once the signal starts to disappear and come back again, there's a sudden jump in the time solution. So 200 nanosecond jump in the GNSS time solution. You may not think that 200 nanosecond is much, but for a good clock, that's a large jump, right? We would expect to see jumps on the order of a few tens of nanoseconds, just from the noise in the. But 200 is a lot. So there alone, an alarm should go off that we cannot use this, right? Either our clock is broken, which means you cannot use it, or there's something faulty with the GNSS signal, which means you cannot use it. But what happened in this case, we were just monitoring, and the master student had not yet implemented the smart algorithms. But we see that there is actually a window of a few seconds from this jump appears until the clock control actually starts steering after the, try to follow the incorrect timing solution from the really the marginal GNSS signals. So, and after 2016, in 2016 there were no, as far as we knew, no commercial devices actually implementing any of these, either basic consistency checks or the good local clock consistency checks. But within the last 5 or 6 years, there have been a number of products, commercial products, implementing various kinds of consistency checks, clock checks, and so on. So this is just an example of two devices. One is actually called the GPS firewall. And we've been doing some tests. Thomas tried to hack his way into that GPS firewall in his master's thesis. We didn't think you succeeded, Thomas, but now we actually think you might have. We can talk more about it once the manufacturer have closed that vulnerability. So to come back to why is the National Metrology Institute interested in these things, is because we're really interested in being able to test, do these devices actually work as advertised? And then if you ask, for instance, Spectracom, if you ask them, what are your filters? What vulnerabilities are you proof against? They won't tell you, right? And if you ask them, how have you tested this? They won't tell you. So what they're actually getting by buying their products, we don't know. So then we have to take our white hat GNSS time hacker hats on and do our best or worst. Okay, another countermeasure, and this is what we've been working on together with Statnett, is that you can have clock systems like we have at Justevesne. Statnett could have their own clock systems, right? And they could use their own network to distribute timing. And because now that there are precision time protocols that will give sub-microsecond timing over wide area optical networks. So we wired up an optical network precision time protocol with one cesium clock as the clock source. And we didn't have sufficient networks to set up a redundant network, so we just placed another clock right at the substation in this case. And also the time server also had a local rubidium clock, which is not as good as a cesium clock, but it's still over a time span of a week or so, it should maintain microsecond timing. And then we had GNSS timing as an input. So this time server actually saw 4 different clock inputs, and when things are working, they should all agree, right? And we'd set it up so that we had, the first priority was the timing delivered over network. That's typically what we imagined the configuration would look like. And second priority would be, in this case, would be the local cesium clock. Third priority would be the GNSS timing, and the fourth priority is the local rubidium clock. So you would think this is a belt and suspenders, and what else can you do? Double belt, double suspenders setup, right? So you should be safe. So one should embrace the failures, right? You learn a lot from failures. We had not planned that one of the cesium clocks would fail, because it's a major nuisance. The cesium clock costs $100,000 right? And it takes many months to repair because it has to be shipped not by passenger airplane but special freight airplane to the US. But it failed. But it did not fail in such a way that it stopped giving timing to the precision time protocol server. So timing was available, but from what was no longer a cesium clock, but its internal crystal oscillator that was just free running. So, but still, we should be safe, right? Because okay, so one of the belts snapped. We didn't know, but it did, right? We think that the other belt and the double suspender should still keep things together, but it did not. That's extremely useful to see. Because when we pull out the internal clock measurement data from that time server, it measures all the sources against the internal time scale. What we see is that 3 of the time sources just deviate from the internal time scale, right? And it follows the one that's set as first priority. So it follows the fail clock. Despite, when you look at the data, you know that 3 sources agree on one thing and 1 disagrees. Which should you pick? In this case, and I'm not sure if they still have any good logic. The logic was that you have, as long as the signal is available, you use the first priority, right? So, in this case, it would be much better if the internal selection mechanism would have some kind of zero trust logic. I don't trust any of the sources more than the other. Then it would be easy to pick out that this first priority is really the false ticker. This you have in I don't know if anyone of you are working with a network timing protocol, NTP. There you have the clock selection algorithm built in, which would do exactly this. It would pick out the first priority as the false ticker and not use it. Okay, that's the end of the talk. This is just a screen dump from our latest test of the Galileo open service navigation message authentication. So at least it flags, as you can see here, spoofed messages. So it flags whenever Thomas turns on the Galileo signals on the signal generator and mix or overpower the genuine Galileo signals, it will flag them as spoofed because they fail the authentication mechanism. There are still some loopholes in how this information is actually being used in the GNSS chip we're testing. And then even for those who use the chip in their systems, they could also be careful how much they put trust also in the authenticated data. So I think that's what I plan to talk about, and I'm happy to answer any questions. So the authentication mechanism will not protect against the replay attacks.
When encrypting these signals, this is only to protect against spoofing?
I would think so. So there was a case of a US drone being downed, well, crash landed in a controlled fashion in Iran. Iran claimed they had broken the GPS encryption. of course, nobody would confirm nobody would confirm that if that had been the case. Likely what they did was to jam the frequency where you have the encrypted signal, and then potentially spoof the open civilian signal. But I think that's to protect against spoofing. Yes.
How would you say to maintain maintainability of these kind of systems? Are they able to be back-tested, or is it going to be hardware exchanges whenever vulnerabilities are found in these systems? Do you have any?
I think there are many levels to that. I mean, one thing is the systems up in the satellites. As far as I know, the Galileo satellites are fairly upgradable. They use programmable radios, and you can build, and that's also the reason why some of these features are being put into service and in test phases, and one learns from how they're working and to determine what should they look like in the full deployment phase. So the signal structure and features are upgradable, at least for the Galileo satellites, and likely for the newer GPS satellites, but probably not for some of the old GPS satellites. And then the problem is that your GNSS chip will still have to implement some of the older legacy things, right? In some of the GPS older GPS satellites that are still active, whereas newer GPS satellites have better features. And then for a time server like this, that's I mean, one thing is the clock and the clock measurement system, but it's a Linux PC. So much of the firmware is just perfectly upgradable, and you can implement much better logic, and you can process, you can take data from the GNSS timing chip and build filters, even if the chip manufacturers have not done that. So there's a lot of room to improve these things. So I think the problem is that GPS and GNSS has so far just worked fantastically well. So that there's very much reliance just built in, which one may not be aware of. And also we see that some of the GNSS chips, okay, they have implemented some kind of spoofing flag and jamming flag. And I think in one of the chips you tested, Thomas, you never were able to make it raise the spoofing flag no matter what you did, right? So that's just false sense of security.
Is it hard to build something like this yourself at home if you wanted a really accurate clock? Do you need the GNSS chip?
No, it's not that hard. Well, it depends on what you mean by accuracy. No, but if one part of accuracy is that you have to account for all the internal delays and so on, and you, yeah, but it's not that hard. I mean, and if in fact with sufficiently powerful software-defined radio, you can even build your own GNSS processing. So there are several open source or freely available codes you can use and improve on and so on. Yeah.
How often are these synchronization messages broadcasted?
Thomas.
This question again. How often are these messages broadcast from the satellites?
GPS runs full set of messages every 12.5 minutes, puts in lots of data for about 30 seconds,
And
the rate it transmits.
yeah, and you can also track the phase of the radio
Can you
transmission.
repeat for those watching on the stream? Can you repeat that?
Okay. I'm not sure I've paid attention to the. Every 30 seconds, you said, Thomas. Is that? Yeah. And then some of the navigation information, like the time scale offsets and so on, are broadcast every 12.5 minutes. But then accurate timing receivers will also track the phase of the signal transmission, not just the coded information, but the phase. So in some sense, it's a continuous process. But for an accurate clock, how often do you need to correct? And that depends on the stability of the clock. So for instance, for the cesium clocks here, if you want microsecond timing, it's sufficient to do a manual adjustment a few times per year, perhaps, not even that. So they don't need to be continuously steered by an external reference once they're set. That's but let's say for a rubidium clock, there if you want microsecond timing, if it's in a stable environment, maybe you have to do a correction every day or so, right? And that's becomes cumbersome to do in a manual fashion. But then for crystal oscillators, you have to do a much more continuous steering. Also depending on how stable the environment is and so on. But, yeah. So if you want to go time hacking, the extremists find each other on the net, right? There's a mailing list called Time Nuts. That's where you will find many hobbyists and also professional people building things, right? Well, you may not be a fan of Meta, but Meta has been a big contributor to the so-called Open Compute project, Time Appliance project. So it's an open source, open design approach to building a GNSS discipline clock that sort of tries to leapfrog some of the timing industry players.
Will it be possible to buy those?
Yeah. Well, yeah, you have to Google or whatever. You have to DuckDuckGo.
Well, thank you very much, Harald.